Hello viewers, welcome to Eko Learners Support for WAEC and NECO candidates. I'll be your physics tutor for this class. Follow me as we go through elasticity.
Eko Learners Support, a support program of the Lagos State Ministry of Basic and Secondary Education for WAEC and NECO candidates.
Here we are looking at elasticity. In this part of elasticity, see what we'll be considering. We'll be considering energy stored in elastic material. We'll also do a recap of formulas used in elasticity, after which we will now take some simple calculations that has to do with elasticity. So, in this class, you need to know these things that I'm expecting from you, such that at the end of this class, you should be able to state the formulas used in elasticity. You should be able to describe the energy stored in elastic materials, also solve some mathematical problems that has to do with elasticity. Now, when we talk about elastic materials, it means these are materials that can regain their sizes, their shapes, when a distorting force has been removed. So, there is a characteristic nature of the energy that is stored in them. In solving questions that has to do with energy stored in elastic material, we make use of this formula. Now, don't forget, in your NECO or WAEC question, it can be asked as work done. Remember that work done and energy, they have the same unit. So, if the question is asked as work done or energy, you can use this formula, it will follow suit. From what we have learned, that F equals to KE. If energy stored is half of FE, where F is the force and E is the extension. So F equals to KE, if you replace the value of F with KE, so you are going to have KE times E, which means if you have KE times E, K remains, then E multiplying E will give you E squared. So that's where we got this from. Now, these are the formulas we are going to make use of in elasticity. From the relations that we have from Hooke's law, we know that F has a direct relationship with E. Then we have F equals to KE. Making K the solution formula by dividing both sides by E. So you are going to have K equals to F over E. Also, from F equals to KE, if you are making E the solution formula, divide both sides by K. So you're going to have E will be here, then F over K. That's what you have here. The other part of the formula we are going to make use of is stress, strain, and Young modulus. For stress, force over area. Now take note, this area might not be given to you. It might take you to do some calculation to get the area. Good. So strain. Strain is extension over original length. And I want you to take note of the word extension. When we talk about extension, we are comparing two lengths. There's an original length, there's a new length. The lengths might vary. You can have the first new length, second new length, third new length, and the like. So our extension is a function of the original length. Our comparison is done making reference to original length. So if I want to look at the first extension, if I have these varying lengths, it's going to be L1 minus L0. That is the original length, L0. If I want to look at the second extension, it will be L2 minus L0. So it's with respect to the original length. That's how we calculate our extension. Don't ever say extension is L2 minus L1. These, both L2 and L1, they are new extensions. So you don't compare They are new lengths rather. So you don't compare extension by making use of the two lengths. You make reference to the original length. So the next part, if you look at Young's modulus, we are looking at the ratio of tensile stress to tensile strain. So the value you have in your tensile stress divided by the value you have in your tensile strain will give you Young's modulus. So let me quickly bring this in. The formula for stress is force over area, which is Newton over meter square. So our units here will be Newton per meter square. So this unit, all over extension over original length, this one does not have unit. Since it does not have unit, so Young's modulus retains the unit of stress. So because this one has the unit of Newton per meter square, but this one does not have unit. So your final answer will still be the same unit as that of stress. Now, from this Young modulus, tensile stress, which is force over area, tensile strain, which is extension over original length. Force over area divided by extension over original length gives you force over area times original length over extension. So F times L will give you FL, F times A will give you AE. A times E will give you AE. So let's look at how we are going to apply this formula in solving mathematical problem. Look at the first example. Example 1 says a force of 80 Newton. A force of 80 Newton stretches 0.84 Newton rather. A force of 0.84 Newton stretches an elastic spring from 7.1 centimeter to 9.2 centimeter. Number 1, find the extension. Number 2, find the force constant. Number 3, calculate the work done. Take note, before we solve at all, let's look at it now. The first part says find extension. When they ask you when you hear the word extension, it means there's an existing length, there's a new length. So you are going to compare the two. So let's spot out the existing length. This is the existing original length, and this is the new length. So it means the difference between that will give us extension. Is that not? Good. So force constant from Hooke's law, F equals to KE. Making K the sum of the formula, we are going to have K, which is equals to F over E. So once we have force, once we get our extension here, we pull it down here, we are going to get the value for the force constant. So work done is given as half Fe. So whatever we have, our force is here, then we make use of the extension here, that gives us the work done. So I've given you a preview of how to solve this. Now let's solve. A force of 0.8 Newton, we are asked to solve for extension. The A part says extension is the new length but not original length. This is the old length, L0, and this is the new length, L1. So the difference between 9.2 and 7.1, when you subtract, you're going to have 2.1 centimeter. So the extension here is 2.1 centimeter. The next slide says a force. Look at the details, still the same detail, but we are looking for the force constant. From Hooke's law, which says that F equals to KE. So from here, the force constant K is F over E. When you make K the formula by dividing both sides by E, you have K equals to F over E. So if that be the case, look at this. The value of F is given as 0.84, and the value of our extension from the previous calculation is 2.1 centimeter. Please take note. So you can do it this way or do it this way. I will explain both. This extension is in centimeter. In this case, the extension, which is 2.1 centimeter, if you convert to meter, you divide by 100. You're going to have 0.021 meters. So if you decide to use the extension in centimeter, different. If you decide to use extension in meters, you get your answer, but they will have different units. Take note. So if it is like an objective question in your WAEC or NECO, if your option has any of these units, that will mastermind the approach you're going to make use of. If your unit is in Newton per centimeter, you will retain. All right. So if your unit is in Newton per centimeter, you use this approach. If your answer is in Newton per meter, you make use of this approach. So look at this now. The force is 0.84. What is changing is the value of the extension. If you leave it in centimeter, you have it as 2.1. If you change it to meter, you have it as 0.021. When you use your calculator to divide, you're going to have this. When you use your calculator to divide this, you will have this. So that is your force constant. The last part of example number 1 says that there is a force of the still same information, calculate work done by the spring. Work done is half Fe. This is the force, and this is the extension. And before we proceed, let me ask you this question. What is the unit of work done? The unit of work done is in joules. That's the SI unit. So what's the SI unit of force? Newton. Then what's the SI unit of distance? Meters. So in this case now, our extension have to be in meter. If you use the value of extension in centimeter, you'll be wrong because you will not get your answer in joules. And our answer, once it is work done, has to come out in joules. So in that case now, I'm making use of 0.021 as the value for my extension. I'm not going to make use of 2.1 centimeter because I want to get a value that is in joules, which is SI unit. So I make use of the SI unit of distance or displacement or length, which is in meters. So that's why I go for 0.021 times this value divided by 2 will give me 0.0882 in joules. Let's look at the next example. Another example says the length of a spiral spring is 25 centimeter when a weight of 25 Newton is hanged at the lower end. When the weight is increased to 40 Newton, the length of the spring is 28 centimeter. Calculate, Roman figure 1, the original length of the spring. Then the other part says the force on of the spring. Now look at this question. We don't know the origin of the spring. We don't know the original length. All we just have from the question is that the length is given at when a weight of 25 Newton is added. We don't know what the original length was before, but all we just know is that once a weight of 25 Newton is added, you have the length will be 25. And once you change the weight to 40 Newton, the length becomes 28 centimeter. So we don't have where the original length, where the length is coming from. So this is the first length, the first extension, and this is the first force. This is the second length, this is the second force. So the question is now asking us for the original length, which is L0. So what we are going to make use of now is that we look at the relationship between the original length and all these new lengths. The original length and the new length is making use of extension. Extension, the first extension will be the first new length minus the original length. And the second extension will be the second original length minus the second new length minus the original length. So making use of the word of the force constant, that's K equals to F over E. So from here, since it's the same material, if you are comparing the force with the corresponding extension, it will be constant all through. So which means that F1 over E1 is this K. It's still the same as F2 over E2. It will still give you K. F3 over E3 will still give you the same K. So as the forces are acting, the extension will be corresponding. So that is the approach we are going to make use of. Now let's solve together. So from here now, F1 over E1 equals to F2 over E2. So we are looking for the original length. And from this extension, you know, the first extension is L1 minus L0. and this second extension is L2 minus L0. Look at this relationship. When you put in the value, the first force is 25 Newton. Look at this. A weight. That weight is force. That is the first force. And then this is the first length, L1. So you replace L1 by 25 with 25. Then you go to the second force. The second force that is acting, that is the second weight, which is 40 Newton. It's going to give us a new length, which is 28 centimeters. Look at it. Replace L2 with 28. So when you cross multiply, 25. Now what happened here is this. This is numerator. This is numerator. So 5 here gives you 5. 5 here gives you 8. So cross multiply. 5 multiplies this. That's going to give you 5 times 28 minus L0. Then 8 times this. That's 8 times 25 minus L0. That's what you have here. So in this case, when you multiply 5 times 28, when you multiply 5 by 28, you also multiply 5 by L1. Then 8 times 28, you multiply 8 by 5 by L0. This 5 is not here. So 8 times L0. So once that takes place, you are going to have 5 times 28 should give us 5 times 8 is 40. 5 times 2, that is 10 plus 4, that is 140. Minus 5 times L, that is L0, that's 5 L0, equals to 8 times 25. That should be 200. Minus 8 times L0, that is 8 L0. So when you do this, you bring this 8 L0 here, you're going to have 8 L0 minus 5 L0 equals to 200 minus 140. So 8 L0 minus 5 L0 will give us 3 L0. 200 minus 140 will give us 60. So you will now say 3 L0 over 3 L0 divided by 3 equals to 60 divided by 3. This 3 goes for 3. You're having L0 left. 60 over 5 will give us 60 over 3 will give us 20. So the original length now is 20 centimeters. So that is how to solve this. The next part, example, the second part of example 2 is that we are looking for the force constant of the spring. The force constant from Hooke's law, which says that F equals to KE. So dividing both sides by E, you have in K. K equals to F over E. So if K equals to F over E, remember that I have told you that for any material, the force constant K equals to F1 over E1 is same as F2 over E2, same as F3 over E3, and so on. I want to prove that to you by using this example. The first case is F1 over E1. Second case, F2 over E2. You see that we arrive at the same answer. How? The first extension will be L1 minus L2, and L1 is given as 25 centimeters minus the original length that we just calculated, which is 20. 25 minus 20 is going to give us 5. So our extension is 5. So that means 25, the force that produced this is 25 Newton, and the extension here is 5 centimeters. So this is going to give us 25 over 5. That's going to give us 5 Newton per centimeter. The same thing happens here. The new length, the second new length is L2, which is 28. 28 minus the original length that we calculated just now is 20 centimeters. 28 minus 20 is going to give us 8. Then, what will be the numerator? That is F2. And F2 is 40 Newton. That's 40 over 8. 40 divided by 8 is 5 Newton. That is Newton per centimeter. So you can see that the relation which says that K equals to F1 over E1, F2 over E2, F3 over E3, F over F4 for the same material, you can see that relationship is valid from this question. Let's also check example number 3. A metal wire of length 26 centimeters. So this is the length, and diameter 2.0 millimeter is stretched. So this can be said to be the original length by a force of this. This is the force that is acting. This is diameter. If the force constant of the wire is this, so this is called K, and pi is given as this, the extension, calculate the extension of the wire, then the tensile stress and tensile strain of the wire, the Young modulus of the wire. So from here, how do you calculate extension? Extension is E. Remember that F equals to KE, which E is equals to F over K. If E is F over K, what is our F? The force acting, that is 400. 400 over K. K is 5,000. So with that, we'll solve it. Let's look at our stress. Tensile stress is given as force over area. Tensile strain is extension over original length. So we have an idea of what we want to do. Then Young modulus, whatever we have here, divided by whatever we have here, that will give us Young modulus. So let's go and solve now. So second part of the example 3, we are asked to calculate the stress, the tensile stress and the tensile strain. So this is the tensile stress, this is the tensile strain. Now look at this. From tensile stress, it's force over area. And area is not given. Remember, you are given diameter. That's telling you that it's a circular object. So from there now, you can get, you remember radius is diameter over 2. So that's going to be 2 millimeter over 2. That is 1 millimeter. And then in meter, that's 1 times 10 raised to the power minus 3 meters. So in that case, area is given as pi r squared. That's 3 points, because 22 over 7 is 3.14 approximately, times 1 times 10 raised to the power minus 3 all squared. So when you multiply this, it gives you 3.14 times 10 raised to the power minus 6 meter squared. So the area we got here now, we just move it here. That's force over this area. The force here is given as 400 Newton. 400 over this value will give us this. So this is our tensile stress. The tensile strain is given as extension over original length. What is the extension? The value of extension we got was 0.08 meters. And this length is given as 26 centimeter. So since length is given in 26 centimeter, we cannot compare centimeter and meter. So what do? We'll bring this one back into centimeter, or bring centimeter back into meter. Whichever one you do, you still get the same answer. Only that you let the unit you are comparing to be the same. So in this case now, if you multiply by 100, you have 8 centimeter. So which means that 8 centimeter divided by 26. When you do that, you're going to have 0.31 as the answer. Now, look at this. The latter part, which is the last part of example number 3, asks us for Young's modulus. So, what is Young's modulus? We are comparing our answer, the ratio of the tensile stress to that of the tensile strain. So, you look at the value we have here as tensile stress. Our tensile stress is given as 1.27 times 10 to the power 8, and tensile strain is 0.31. So, when you divide tensile stress divided by tensile strain, you are going to divide this value by this. Once you divide, you have this value. So with this now, you have the value for the Young's modulus. Now, I want you to take a glance at what you have on the board. This is a way of checking up whether you have actually, or you can remember all we have just done. So I'm going to give you like 2 minutes to go through all of this, and whatever you have, we will bring it, then we'll compare scripts.
Eko Learners Support, a support program of the Lagos State Ministry of Basic and Secondary Education for WAEC and NECO candidates.
Alright, so I'm back. Let's look at it together. Question number 1 says, the ratio of tensile stress to tensile strain is known as what? A. Modulus of rigidity. B. Modulus of elasticity. C. Young's modulus. D. Shear modulus. So in this case now, remember that we have just done it. Young's modulus is the ratio of tensile stress to tensile strain. So which is the correct answer? Okay, the correct answer should be what? The correct answer is obviously Young's modulus. The SI unit of tensile stress is what? Yes. What is the SI unit of tensile stress? Okay, let's check together. Tensile stress, what's the meaning of tensile stress? What's the definition? That's force over area. What's the unit of force? Newton. What's the unit of area? Meter square. So Newton per meter square, and that is option C. So the correct option is option C. All right, let's look at the third question, which says that from Hooke's law. Okay, Hooke's law states that. So what can you say about Hooke's law mathematically? If you don't know it, if you cannot recall it, then state it, you pick it. So extension produced has a direct relationship with the force that is causing it. Now, that is F is proportional to E. So let's look at the option, which one has this relation. So that is F, that is proportional to E. So that is option B. That is the correct option. The last part is asking us to calculate what length of the spring we are going to have at 3 Newton if Hooke's law is obeyed. So if you look at this question, let's quickly go through it since we have attempted it, so we will not waste too much time. So from here, you are going to have the spiral spring of spring balance is L0 when this, so this is L1, this is F1. So from here now, we are going to have another one. This is L2 and this is F2. What is the length of the spring when this you're having this? So from here you can go like saying K equals to F1 over E1, which is F2 over E2. So K, using the relationship of this K, we are going to have F1 over L1 minus L0, which is F2 over L2 minus L0. What is F1? F1 is 5 over L1. L1 is given as a 25 minus L0, which is F2. F2 is 10 over L2, which is 30 minus L0. So from here, 5 here 1, 5 here 2. When you cross multiply, 2 into bracket of 25 minus L0 equals to 1 into bracket of 30 minus L0. So when you do this, you're going to have 50 minus 2L0 equals to 30 minus L0. So from here, you're going to have 20 equals to L0. How? 50 minus 30 will be equals to 2L0 minus L0. 50 minus 30 is 20. 2L0 minus L0 is L0. So original length is what? 20. So our extension is given as L. You can say your extension is given as extension 1. That's L1 minus L0. That's 25 minus 20. So our first constant is given as F over E, which is for the first case L1 over F1 over E1. So F1 is the first force is 5. Then the first extension is also 5. So our first constant is 1. If our first constant is 1, they said what is the length that we are going to have here. So from here we are going to have extension equals to F over K. Which force is acting? That is 3 over which the first constant is 1. So you are going to have the 3 as the extension. If 3 is the extension, then our extension is equals to the length we are looking for minus original length. So extension plus original length will give us the length we are looking for. So the length we are looking for now will now be extension plus original length. That's 3 plus 20. So this gives us 23. So the correct option is option D. So D is the correct answer.
Eko Learners Support, a support program of the Lagos State Ministry of Basic and Secondary Education for WAEC and NECO candidates.
Answer. I hope you have gained something from this class, and then I want to put it to you. If you have any question, observation, or comment or suggestion, kindly forward it to our social media handle that is displayed on the screen. Thank you.
Acing your WAEC and NECO examinations has been made easy by the Lagos State Ministry of Basic and Secondary Education with the Eko Learners Support for WAEC and NECO candidates television program. Join seasoned teachers as they take you through these core subjects: mathematics, English language, physics, chemistry, and biology, targeting the exact syllabus of WAEC and NECO. Watch Eko Learners Support for WAEC and NECO candidates on this station. Learners can also connect with Eko Learners Support for WAEC and NECO candidates through these social media platforms to access more educational content and give their feedback. Eko Learners Support for WAEC and NECO candidates. Pass your examinations with flying colors.